Hello students, welcome back. Today we'll be working on solving some differential equations, and we're going to do this by a method that is called separation of variables. This is when you have x's and y's in your equation and you have to solve the differential equation. Now, our problem number one on this set of notes looks like a y. That's actually a y prime. So make sure you know that that is y prime. And I'm actually going to rewrite that using the dy dx notation. So dy dx equals, I'll go ahead and change the square root of x to x to the 1/2 over 3y. Now, we have both x's and y's, so we'll need to get the y's on one side, the x's on the other. So we can multiply by 3y, and that'll give us 3y dy, and then separate the dx over to the other side, having x to the 1/2 dx. And then to solve a differential equation, you integrate. So we'll integrate both sides, and we can do the power rule for this one. So we would have 3y to the second over 2, and we'll put the plus c on the side with the x. So on the side with the x to the 1/2 would we would add 1 to that exponent, and so you're going to get x to the 3/2 power, and then this is over 3/2, and this is the side that we will add c. Now the 3/2 can be changed, the one that's in the denominator, so let me go ahead and rewrite. We've got 3/2 or 3y squared over 2 equaling, and then this 3/2 will become 2/3, and then we'll have x to the 3/2 power, and then plus c. We can multiply by the reciprocal so that we would get y to the second equals, multiplying by the reciprocal would give us 4/9, and then x to the 3/2 power plus c. And then we'll need to square root both sides, which then would give us y equals, the square root of 4/9 would be 2/3. Don't forget, you'll get plus or minus. So plus or minus 2/3, and then we'll have to put a square root around our x to the 3/2 power. The square root will not affect the plus c. So that would be the way that we'll state your final answer. I would like for you to take your equations to y equals. So we want to solve our equations for y. So you'll have some differential equations where you separate the variables, and you'll be able to solve for y in that way. And then our second problem, you'll see that we get a logarithm involved with it. So for the second problem, we cannot add y to both sides. So that is not a technique that can be used. We have to think of this as a grouping of 4 minus y. So I'll start by separating and having dy equals 4 minus y dx. And then I want to get this to the other side. So I'll divide by that 4 minus y, making dy over 4 minus y equals dx. And then this is what we will integrate on both sides. So we will integrate, and on this side with the 4 minus y, we'll have to use a u. U would be 4 minus y. Your du would be -1. dy. So we're going to need a -1 and then a -1 on the outside, so that we have the -1 integral of 1 over u, and then the -1 dy would be the du, equals, and then the integral or the antiderivative of dx is x, and we'll have the plus c on that side. Now, we're going to do quite a bit of work to this. So we do the antiderivative, we get -1, and then this is the natural log of the absolute value of the u, and our u was the 4 minus y. And then that equals x plus c. So now we're going to go through the process of solving for the y. The first thing you want to do is get the natural log by itself. So we'll need to divide both sides by -1. That's going to give us natural log of absolute value of 4 minus y equals, and then the -1 will affect the x, but you'll just have plus c. So -x plus c. And so now we're ready to convert this to an exponential. So your base is e, your power is the -x plus c, and we're going to work with the positive 4 minus y and not have the absolute value. So then I'm going to use a rule of exponents in reverse of how we normally use it. So remember that when exponents are added together, that's because they came from a multiplication of something with the same base. So what I've just written here is equivalent to the line above. If I have the same bases, I add those exponents and keep my base. And what happens is that this e to the c power is actually a constant. And so we will call that constant c, and then have the rest of our statement ce to the -x equals 4 minus y. And then from here, we're going to solve your equation for the y. So we could add y to the other side, subtract the ce to the -x, and that's going to end up giving us y equals 4 minus ce to the -x power. So you're going to have several situations in your work where you get a logarithm. When you get that logarithm and make your conversion to an exponential, you're going to drop the absolute value, and that's because the exponential can only equal the positive, and then get the y by itself by converting your e to the constant as your constant c. And so that'll be a way that we will write the solutions to this type of differential equation. Now, we're going to move on to a statement that will then become a theorem. In many applications, the rate of change of y, and so the rate of change is your derivative, is proportional to the y. So in other words, the rate of change of y with respect to x is equal to some constant times that y. And so this is where your growth and decay model that maybe you've recognized from Algebra 2, y equals ce to the kt power, that comes from this relationship, that the rate of change is proportional to that original amount. And so it says if y is differentiable, it's a differentiable function of t such that you have a positive value for y and y prime. And again, this y prime is our dy dx. So dy dx equals k times y for some constant k. Then your equation y equals ce to the kt will be your exponential growth or decay model, and c is the initial value, and k is that proportionality constant. I don't normally do this, but I'm actually going to do a proof, or at least an algebraic proof of this theorem. And then once I've done this proof, we'll just be able to use this proportionality constant or proportionality equation and not have to go through the derivative process every time. So our given statement is this statement right here, except I'm going to write it as dy dx. So, and again, you can't see that very well, but that is y prime. So dy dx, sorry, it's not dx, it's dy dt, because it is proportional, or it is a rate of change with respect to time. So dy dt would equal k times y. It's proportional. The rate of change of y is proportional to y. So we're going to separate our variables. I need the y on the same side as the dy. So I can divide both sides by y and have 1 over y dy equal to, and then I'm going to separate and bring that t dt over with k. So k dt. And then we will integrate on both sides. And the integral of 1 over y is the natural log of the absolute value of y. And that equals, and then we have k, so its antiderivative is kt, and then plus c. So in solving for the y, I will have e to this power kt plus c equals my positive value of y. And so then this will give me y equals, I can use that exponent rule in reverse, e to the kt times e to the c power, and then this becomes c. And so y would equal, so this is where I'm getting my c from, c and then e to the kt power. So if you start off with an equation where it says, or with a statement that says the rate of change is proportional to the amount or to the same variable, then you can use this rate of growth or decay model and not have to go through all of this process of doing the derivative and solving it so that you end up getting this. So we've proved it, and now we can use that relationship. So just a very basic example would be a statement like this. The rate of change of n is proportional to n. So when these are the same, then you can use that model. I'll go ahead and write it so you can see it. So the rate of change of n, and my other variable is t. So with respect to time is proportional to n. That's what this statement says. Because of that, I can use the decay or growth model, which says, and now I'm going to use n instead of y, equals c e to the kt power. And so that I can go from here to here without doing any calculus. And then after that, hopefully it'll come back to you how to solve with these models. Basically, I like to use ordered pairs. Time is your x, and then whatever the other variable is, that will be your y value. So we'll start off with a time of 0, and when time is 0, this n is 250. And I'll show you another thing that always happens that you can use. So we'll put 250 in for n, and that equals c. I don't know the initial amount. E. I also do not know the constant k, but I know the time is 0. Well, so that gives me 250 equals c, and then this is e to the 0 power, and so that's just 1, and so my c is 250. So if you are given an amount at time 0, then this amount at time 0 is going to be your initial quantity. So if you're asked to find the initial quantity, if you are given an amount at time 0, that would be your initial quantity. Sometimes you're not given that, and then you have to employ other algebraic techniques like systems of equations, or I'll do an example of a half-life model and give you another idea of something you can do. Once you know the initial quantity, then you can make a substitution. So now I'm going to use the 1 and the 400. And I'll have n equals, and I've got my 250 e. I'm going to switch back colors. 250 e to the kt power. I can substitute in 400 for the n, then 250 e. I still don't know k, but I do know my time is 1. So now I have just e to the k power. I can divide both sides by 250. So 400 divided by 250 would give me 1.6 equals e to the k power. And then I can solve that for k by using a logarithm. So k is equal to the natural log with a base of e of 1.6. So I get my constant is a natural log of 1.6. If you are asked to give your equation of your exponential model equation, then you have to know both the k and the c. So I now know both of those. My exponential model would be n equals 250 e to the, and then my natural log of 1.6. You can get a decimal for that if you want to, or you can just leave it like that. Be sure you store values. So the natural log of 1.6 and then t. That would be my exponential model. And then using that, I finally have this last question. When t equals 4, so when the time is 4, I can substitute n. So I'd have n equals 250. Whoops. So 250 e. My exponent is the natural log of 1.6. And then my time is 4. I can substitute that in. And in doing that, we get, and this will be an approximation, 1638.4. And if it had units, sometimes those would be grams or whatever the problem might be about. So 1638.4. So you notice that you've got several things to go through in order to find all of your variables in your model. If you'll turn your paper over, I've got one more example that I'm going to go through with you. This is a half-life model. Often we use that exponential growth or decay with half-life. So notice up here it says radioactive decay is measured in terms of half-life. This is the number of years required for half of the atoms in a sample of material to decay. And then here's your statement that lets you use the model. It says the rate of decay, and this is of the material, is proportional to the amount present. So that is a statement that would basically say dy dt, whatever that y is equal to the k times the y. So we can instead use then y equals c e to the kt power. So we'll be able to use that exponential decay model. So the first thing it wants you to do is to find the initial quantity. So notice that you do not have that information. You know the half-life. You know how much of carbon-14 is there after 1,000 years. But you do not know how much is there at the beginning. So to find this initial amount, I'm going to use this half-life information and realize that if no matter what amount I started with, and make sure you use, this is time, even though it's the bigger number. So 5,715 years, half of whatever I started with would be there. Then that means at time 0, all of it would be there. You can make this number whatever you want and then just double it at time 0. But we'll need that information to help us find this initial amount. So I'm going to use my y equals CE to the KT power, and I can substitute in the 1/2, and then I don't know a value for C, but I'm gonna start with an initial amount of 1 so that I can find my value for K. So E to the K, and then my time would be the 5,715. So this is so that I only have the one variable. And so I can solve for my exponent using a logarithm, 5,715k, would equal the natural log with a base of e of 1/2. And then dividing, I can get a value for k. So k would equal the natural log of 1/2, and then divided by 5,715, and that's approximately negative 0.000121. So after I know my value of k, now I can start working on finding the actual value for the c. So now I can use my given information that after 1,000 years, should have an S on it, after 1,000 years, the amount of carbon-14 is 1.6 grams. So remember, 1,000 is the time, 1.6 grams is the amount. I can use my value of k and make my substitution. So the y would be 1.6 equals, I'm looking for c, the actual initial amount, e, and then using my value of k, and I do want you to use stored values. So negative 0.000121 t. I can, excuse me, I do know the value of t. My t is 1,000. And so to solve this for c, I can divide both sides by this amount. This is an amount to that I can divide by. And so my c will equal approximately 1.806. So again, taking both sides of the equation and dividing by this. So I'll put divide on both sides, so that way you can know what I did there. So C is approximately 1.806, and that would be that many grams. So let's think about what's going on here. After starting with 1.806 grams, after 1,000 years, 1.6 grams are left. It would take 5,715 years for half of this amount to be left. All right, then part B asks you to write a model equation. Whenever you're asked that, we want you to substitute in C as well as K. So this is your C value, 1.806. And then E, our K value is negative 0.000121 T. So there's your model equation. And then our final question is, what is the amount after 10,000 years? So the 10,000 is a T, and we simply need to substitute in. So 1.806 e to the negative, and notice that negative exponent does mean that it's in a state of decay. And then your T value, which is 10,000. And you can certainly use calculators. You'll need it all the way through on this. And so this is just a straight calculation. And so Y would equal 0.537, and that would be grams. So notice that after 10,000 years, definitely more than half of this is gone. So, in fact, almost twice as much. So, we will be doing some separation of variable problems on your homework. And then you're going to be working out some problems that really don't have calculus, but they're based on the fact that this rate of change is proportional, and that lets you use this model. And so I want us to just review. These are great problems that actually come up in some real life applications, and I'd like for you to work on those. So this will be homework 59, and be sure that as you have questions, you seek some help.